In this section of chapter 10, we'll talk about naming of carboxylic acids and its derivatives. In naming a compound, again, just like before, you need to select the longest carbon chain that must contain the functional group. In this case, functional group is C double bond OOH. So for example, if you're looking at this compound, the longest chain is this. So let me use another pen color. So that's the longest chain. I'm showing you with number 1 through 4. Now that's the longest chain, and also that contains the carboxylic group. This is the carboxylic group, C double bond OOH. So that's the carboxylic group. So once I got the longest chain, and functional group has to get the smallest number. So that's why my 1 starts here. So 2, 3, 4, and the third location you have a methyl group. So this is the methyl group. So that's why I say 3-methyl, and we have 4 carbon. 4 carbon is butane, and this would be butanoic acid because functional group is not alkane. It's a carboxylic group. So it's a butanoic acid, OIC at the end. When it's a ring compound having carboxylic group attached, then the naming would end with carboxylic acid. For example, this compound, you see, again, this particular carbon and the ring gets 1 because it holds or attaches to carboxylic group, COOH. And the fourth location, there is a chlorine, so that's why I say 4-chloro cyclohexane. So this is cyclohexane carboxylic acid for this. The first compound is acetyl chloride, and the second one is called benzoyl bromide. So the corresponding acid is benzoic acid, OIC acid. The third compound is cyclohexane carbonyl bromide. Corresponding acid name is cyclohexane carboxylic acid. So these are the acids. Acetic acid gives you acetyl chloride, benzoic acid gives benzoyl chloride or bromide, and then cyclohexane carboxylic acid would also have similarly named close to its acid. Now acid anhydride has this kind of functional group with 2 carbonyl groups. So these are the 2 carbonyl groups and a COC. So both ether linkage in addition to carbonyl groups. That's called anhydride. How do we get anhydride? If you have 2 acetic acid, for example, water molecule gets out of it, 2 OHs, and then instead of that, when water escapes, then you get this functional group and makes acetic anhydride. Amide. Amide has the functional group of C double bond ONH2. Again, the names of these compounds have similarity with the corresponding name of acids. For example, if you have like benzoic acid, it would be called benzamide. So you remember benzoic acid? Let me show you the structure. If a benzene ring, that's benzene ring, COOH, that's benzoic acid. So benzoic acid. But when you get corresponding amide, it's going to be benzamide. So this will be C double bond O, and instead of OH you'd have NH2. So that's called benzamide. So here now naming would be simpler. From acetic acid, you can write down acetamide or acetamide. Butanoic acid, this is butanoic acid, the bottom one. Butanamide is the top one, CONH2. Again, OH is replaced by NH2 in this case. Then cyclohexane carboxylic acid is shown on the right hand side. Its corresponding amide is cyclohexane carboxamide. Now naming of ester. Ester has the functional group of C double bond OO and an alkyl group. That's ester. The one specific example is given here, CH3COO CH2CH3. In naming these esters, first you name the group that is bonded to oxygen. So that's CH2CH3, and that's ethyl. Since it came from acetic acid, its common name is ethyl acetate. If it's a more systematic naming, then ethyl ethanoate. Ethanoate comes from the fact is this acid is also called ethanoic acid, having 2 carbon in the longest chain. Methanoic acid, ethanoic acid, propanoic acid. So this is ethanoate is the ester. So you see here. In this case, you get T-butyl group, and I already highlighted the T-butyl group. In case you don't remember it, is here, is this. This carbon is a tertiary carbon. That means that carbon is bonded to 3 other methyl groups, or carbon, and that makes it T-butyl group. So T-butyl cyclohexane carboxylate. So how do I remember that name? Remember that without this T-butyl, it will be carboxylic acid. Corresponding acid will be carboxylic acid. And obviously with T-butyl, it will be tertiary butyl cyclohexane carboxylate. CN group is called nitrile, C triple bond N. So again, you need to get the longest carbon chain that contains the functional group, which is C triple bond N. And so my number starts from this carbon that is bonded to nitrogen, or the functional group. So in the 4th location, there is a methyl group. So this is the methyl group. So you have to say 4-methyl, and there are 5 carbon compounds, pentane, and then just at the end you write down nitrile. Similarly, you can see some of the common names. Acetonitrile, instead of acetic acid, you get acetonitrile. Instead of benzoic acid, this becomes benzonitrile. So if you remember the name of corresponding carboxylic acid, its naming of these kind of compounds would be much easier. So the last one is 2,2-dimethyl. This is 1 methyl, this is the second methyl. So 2,2, this is 1 because it contains the functional group. So this is 2,2-dimethyl cyclohexane carbonitrile. Instead of saying carboxylic acid, which is the corresponding carboxylic acid. The common names you should definitely remember, especially these common names, acetic acid, benzoic acid. These are so common and so commonly used compounds in organic chemistry. I strongly suggest that you know these names. Properties of carboxylic acid. Carboxylic acid, usually 2 molecules. Let me show you this separated. This is 1 molecule. This is the second molecule of carboxylic acid. They are bonded together. We call it dimer. Dimer means 2 molecules cling together through this kind of bonds, which we call hydrogen bond, where hydrogen acts as a bridge binding those 2 molecules together. Now, I would like to give you some idea about the sources of acetic acid. In vinegar, you get acetic acid. butanoic acid. When butter gets bad, you'd find butanoic acid. Here we're looking at some of the reactions, and you can see basically this is an acidic reaction where H plus is one of the products, and we have defined pKa value at the beginning. And in case you didn't remember, I want to emphasize that a smaller pKa value means a stronger acid. So larger pKa means weaker acid, because pKa is defined by log of inverse of Ka. For stronger acids, Ka value is larger, so obviously the fraction is going to be smaller. So pKa value small means a strong acid. So now here I have two different acids shown, one having pKa value of 0.64, the other one has a pKa value of 4.75. So obviously the acid with pKa value of 0.64, which is smaller, significantly smaller than the acid shown on the top. So 0.64 represents a stronger acid than the acid that had a pKa value of 4.75.